Okay then, this week we are going to be talking about state-independent contextuality. Okay, very well. So in our previous lectures, we had talked about introducing a set of measurements. These are just abstract measurement labels. Maybe there's n of them, and then a set of outcomes. And we also talked about a collection of contexts, but let's just keep this to okay. And within this setting, we were able to talk about a global value assignment G, which is a function x to O. And so what is this thing doing? It's taking each little xi in my set, and it's assigning it a predetermined value, say some OI. Okay. And we were able to talk about something like an empirical model E. Model E is classical if and only if we have that E is in the convex hull of these deterministic behaviors. Okay, so essential to this definition of classicality is that we can even define these G's in the first place. And so the topic of state-independent contextuality, if I sort of had to approach it from a very high level, there's some fine print that we're going to get to momentarily, but the crux of it is that you kind of can't even define functions like this when is this the case? When the measurements that you're talking about are related to quantum observables. These quantum observables are not just abstract labels. These are self-adjoint operators, and they satisfy certain additional algebraic relations that we'll get to. But the idea is that when your set of measurements consists of quantum observables, and there are a sufficiently rich set of them, it's not going to be possible to always identify an outcome to each of them in a consistent way. And when that's not possible, you can't define something like a G. Later, we're going to call this a value assignment in the case that there are some additional functional relationships that are to be satisfied that are not present here. And then if you can't define G, you can't define a deterministic behavior. And if you can't do that, then you can't define what the non-contextual sort of set of empirical models even is. So state-independent contextuality is somehow, in relation to our previous discussion of hierarchies, it's somehow the most extreme version of contextuality that you could think of. So we will answer the following question in the negative, which is, does there always exist a global for quantum observables? So this is sort of the organizing question of today's lecture. And I put global outcome assignment in quotes because there's some structural differences in just this simple map here as opposed to the equivalent notion of a value assignment that we will introduce momentarily. So maybe we just get right to it. As I mentioned, this will be answered in the negative, and so there's a couple of different examples. The Peres-Mermin square, there's Kochen and Specker, and their original proof, which we won't go through in full detail, but there is also that using 117 vectors or whatever the number is. So okay, so I'm going to talk briefly about the algebra of observables. So we all sort of recall that, so let's fix some Hilbert space finite dimensional for some dimension d, that a observable is a self-adjoint operator A equals A dagger. We say that A is Hermitian. And there's a couple of properties associated with these Hermitian operators. So one is that they have a spectral decomposition, the eigenvalues AI, and the projectors onto the corresponding eigenspace, where pi I, pi j are orthogonal, delta ij, pi I. If we wanted to, for instance, and maybe I'll write this as number 2, we can define functions of an operator as defined through functions of its eigenvalues using the same set of projectors. Let's just leave it as I. So we will not necessarily need to think at the moment of these as being rank 1 projectors, but suffice to say that there will be a couple of cases later on where we will want to think of these as being rank 1. So going further, if you have that A and B commute, so if A and B commute, then we can actually also define A times B, and I claim that A times B is also going to commute with A and B, and you can sort of just see that. So define AI pi I, and say that B is given by sum over J, Bj, and these are the same pi's as appear over here, over J. So we expand this sum, just a double sum, AI, Bj, pi I, pi j, but these are satisfy this relationship, so you just get AI, Bi, pi I. So if A and B commute, then you also have that A times B is another Hermitian operator who has eigenvalues A times B. So this sort of structure, the fact that Hermitian observables lead us to a spectral decomposition, we can define measurements in terms of these corresponding projectors, and so we get the outcome AI when we do a measurement with probability given by the Born rule using this pi in some quantum state. We get the same probabilities for f of A as we do for A, but with different eigenvalues. And in fact, if A and B commute, then we get still something similar. And you see that A and B is also going to be compatible. A times B is also going to be compatible with A and B. So there's a sort of closure property here. And so that's why I put this as being an algebra of sorts. You can add things together. So continuing on, you might be able to say something like 3 prime if you have A1 to and commuting, then you can obviously define some c equals a function of a1 to an in a manner similar to this. And so one point of deviation from our previous discussion of what it means to define classicality, recall that this definition here of sending these set elements to some outcome was how we were defining something as being predetermined or classical or non-contextual. We would like to do something similar. We still want to assign values to our observables. That stays the same. But we also want to respect the fact that our measurements are not coming from just these arbitrary set elements. I mean, there's no notion of multiplying these set elements or adding them together. There's no structure here. They're just labels in some sense. Whereas here, we really have some additional structure. And so we want to define a notion of classicality. So maybe we say this here. We wish to define a notion of a classical, or rather non-contextual value assignment that respects algebraic relationships among observables. What does that look like? Okay, so the way we want to talk about this I'll be a little bit loose for a second, just to give the idea, but this is maybe should be in question or in quotation marks. So we want to morally do something like this. We know that the observables that we have in quantum mechanics are coming from Hermitian operators, and we would like to be able to assign them real outcomes. So this is sort of what we expect in quantum mechanics, and so this is very similar to what we're trying to do there, morally speaking. We'll see actually that this is not going to be possible. So how would we like to do this? Well, it's not enough to just send each operator to some real value. We would like it to also reflect some physical property, namely, we want that the value that it gets is coming from the spectrum of that operator. This way, we know that we are reproducing what happens in quantum mechanics. When we do a measurement, we get one of the eigenvalues with some probability. And we are essentially at some base level trying to understand, as we were before, whether it's possible to reproduce the statistics of quantum mechanics by assigning definite values to observables. You can imagine that we can't do this, but let's see if there's a sort of more refined way to define what classicality is in this case, and then see how it's inevitably violated. So what other conditions should this value assignment satisfy? Well, what does it mean to say that it respects algebraic relations amongst observables? So what that means is, for example, if we have an operator b is equal to f of a, then we want the value that we assign to this, v of b, to be equal to f of v of a. Okay, because what is v doing? V is picking out an eigenvalue from the spectrum of A. So if we define if B is a function of A, then the eigenvalue picked out by B should be a function of the eigenvalue picked out by A. Seems natural. For sets of commuting operators, A1 to AN, if these commute, then, and we have f of, sorry, it's the other way around, as you could probably imagine. If you have b is equal to f of a1 an, then we want, in general, then we want v of b equals f of v of a1 v of an. For example, this function could just be a sum. We'll see later that an example of this is when a1 to an, or some of the operators are projectors, such as these. They commute, and you can think about taking the sum of them. The sum of them, when they're in a PVM, should equal the identity. That's a functional relationship that we'll take advantage of. This could be a product. So if I have one operator that commutes with another and you take the product, then the value v of ab should be the product of the values of the eigenvalues of each. Another sort of interesting point, so maybe a couple of them to point out. Let's say let's call this a remark, because the other one will be a remark. So the first is that this notion is, and by this notion I mean the function that we're defining here, v, is non-contextual. Okay, how can I see this? One way to see it is that there's a single function v going from Hermitians to R. So in particular, for any given A, regardless of whether A is grouped together with a particular set of other operators B, C, and D, which it commutes with, or whether it's grouped together with some other operators B prime, C prime, D prime that it also pairwise commutes with, the value of A, v of A assigns just one specific eigenvalue. So you do it once and for all. There is not a collection of these, it's just once. We just pick one function, Hermitian H to R. And in this sense, it's non-contextual because you just are assuming that you use the same eigenvalue throughout the whole calculation. Once you've picked it once, it doesn't matter what context you put it in, it will always be the same value. So first, it's a non-contextual assignment. And then the second thing that I was going to say, but it suffices maybe just to point it out more explicitly now, is that, again, I want to reiterate that these global outcome assignments, which I'm trying to use a different name to make or put emphasis on the fact that these are not exactly the same thing. I suppose you could think of the non-contextual value assignments that we're defining here as somehow being a special case of these. But this is somewhat more general in that, again, you don't care at all about the algebraic structure of the operators or the measurements involved. So let's do an example. Okay, so this example is known as the Peres-Mermin square. The crux of the Peres-Mermin square is that we are going to use these very easy to analyze operators, single, well, maybe I should say this first. Well, it changes. I will first say that we'll define the Pauli spin operators, which may hopefully be familiar to most, are for a single two-state system. So we have x, we have y, I0, minus 1. And these operators satisfy certain properties, which are quite nice. We have that, well, I will write them collectively as sigma. Sigma dagger equals sigma, so they're Hermitian. Well, I'm getting ahead of myself. Sigma squared is equal to the identity. So if you see that this is a permutation, it maps 0 to 1, 1 to 0 for those familiar with quantum computing. Then if you do the permutation twice, you're back to the identity. And the same goes for the rest of these because they're all unitarily equivalent. So this is II. We also have that, well, this second fact also implies that the eigenvalues spectrum of sigma equals plus or minus 1. And we also have, let's say, the following identities. xy equals iz. We have that yz equals ix. We have that zx equals iy. So these are the product relations. Hopefully we can still mostly see these and make ample use of them. And so what is the Peres-Mermin square? It is a two-qubit, a set of two-qubit observables arranged into a square. As follows. We have row 1, row 2, row 3, C1, C2, C3. And I will use the notation, hopefully it will not be too confusing. A tensor B is just equal to A1, B2, which is just equal to AB when there's no risk of confusion. Sometimes I will just make this explicit. Maybe at first I will do that. X tensor I tensor X, and X tensor X. The idea will be that everything in a row is going to pairwise commute. Therefore, they're going to be in a context. They share a joint set of eigenvectors. Everything in a column will also pairwise commute and therefore also be in a context. So here, I tensor Y, Y tensor I, y tensor y. And then we have the product of these is going to be x tensor y, y tensor x. And then this one looks a little bit more non-trivial compared to the rest, but z tensor z. And so the reason the name square comes in is because people usually think of this as 9 observables that can be organized into something that looks like a square. A couple of items here. So let's just compute some stuff about the first row, and then we'll see actually that rows 1 and 2 and columns 1 and 2 are quite similar to one another. And so once we do one, it'll give you an idea of how to do the others. The other contexts that are a little bit harder to see maybe at first sight are precisely row 3 and column 3. So row 1, what we sort of want to show is first just that these things pairwise commute. It's not too difficult to see this. The idea will be if you do xi dot ix, this is equal to xx. Whereas if you do it the other way, ix dot xi, this is also equal to xx. And so you have that it commutes. xi ix is equal to ix xi. We also have that the product xi dot ix dot xx is equal to x squared on the first tensor factor, x squared on the second tensor factor. We know that those are identity, so we have I tensor I. And something similar follows for R2. The product of those are also going to, they all pairwise commute, and then their product is the identity. Let's just say I. Similarly, C1 and C2 as such. Let's continue over here for just a moment. R3. To see that these, so xy dot yx is going to be equal to xy tensor yx, which is going to be equal to iz tensor minus iz, which is equal to just z tensor z. Doing it the other way around, we actually find that it's also the case that yx dot xy is also equal to z tensor z, and that the full product xy dot yx dot zz is equal to positive I. Now column 3. So I just showed here that these pairwise commute. Of course, there's a couple of other cases to show, but it's not too much different in terms of the arithmetic. So just bear with me and just we'll assume that it works out. Now column 3 is going to be xx dot yy is equal to xy tensor xy. Now we see that something different is happening here because now we have xy times xy is iz tensor iz, and so we have that this is equal to minus z. Going the other way, we get also that yy times xx also equals to minus z tensor z. And if we just go and multiply through these observables, we get minus I in this case. So now let's assign a classical value assignment. a non-contextual value and the way that this will work is roughly that we will assign an eigenvalue to each of the operators here, and we also want to make sure that these value assignments will satisfy the product relations, namely that many of the products of these are equal to identity or minus identity, so we will make ample use of this. We have v of xi, v of ix, v of xx. Very nice. V of iy, v of yi, v of yy, v of xy, v of yx, v of zz. Very good. Now we want to check to see if this is entirely consistent with our product relations. You might imagine that this is going to be similar to some other computations we've done. Let's see how that works out. Well, let's try this. Row 1, what's happening in row 1? Let's do this in some detail. We have the following product: v of xi, v of ix, v of xx. So many of the other cases will follow just like this. We want to have these value assignments respect the product relations. So this is going to be the same thing as xi dot ix dot xx. But we already showed that this is precisely equal to v of the identity. And the identity has precisely one eigenvalue, so this is equal to +1. Similarly, we are going to have row 2. We have v of iy, v of yi, v of y is equal to +1 through a similar argument. R3, when we looked at R3, we saw that the product is again +i, so no surprises when I write down that v of xy, v of yx, v of zz equals +1. So column 1, we have that v of xi, v of iy, v of xy is equal to +1. Column 2 is similar. V of ix, v of yi, v of yx is also equal to +1. These are all just following from the product relations that we've already written down. And then C3, now this is the different one, v of xx, v of yy, v of zz. Well, let's be a little bit more explicit here. This is equal to v of xx dot yy dot zz, which is equal to v of minus I, which is equal to -1. So in totality, what's going on here? I have 6 sets of product relations, and we can ask the question of whether these are consistent. As you might expect, they're not, and so how does that come about? It comes about because when I multiply all the rows through, I get one of each possible observable. So the value assignment for each observable shows up once. And when I go through the columns, again, each observable shows up once. Xi shows up here once, Ix, Iy, Yi, Xy, Yx, Xx, Yy, Zz. So then when I multiply everything through, I get precisely something like xi squared all the way to, v of xi squared all the way to v of zz squared, which is equal to plus 1. But the right-hand sides, plus 1 times plus 1 times plus 1 is plus 1. Plus 1 times plus 1 times minus 1 is minus 1. So this equals minus 1, which is a contradiction. So this is the well-known Peres-Mermin paradox, in which if you just assign, in I would argue, a very natural way, values to the observables, they cannot reproduce the predictions of quantum mechanics in the sense of being able to reproduce both the product relations, the observable, the algebraic relations between the observables, as well as maintaining their eigenvalues. There is a comment to be made. So there's this thing called Mermin's inequality. So often it is the case, for example, in CHSH, and as we saw that there are rigorous ways to obtain inequalities corresponding to facets of these classical, the boundary or region of classical empirical models. These distinguish precisely which empirical models are non-classical from the classical ones. Mermin's inequality, I'm not sure if it has the same status, but it is a contextuality inequality in the following sense. We had said that what makes something a contextuality inequality is that it's satisfied by all classical models, but violated by some non-classical ones. And so this one has that flavor. And the idea is to define a quantity, which is, and before I do this, actually, I will use the following. I will use the following notation. If I write something like expectation of R, I mean that I am considering the expected value over all triple of observables that are inside of a particular row, for example, or a particular column if I put C. So it could be like some A, B, C. And by bracket, I'm going to mean two different things, as is sort of typically the case. If I want the quantum value of something, these brackets are going to be coming from the Born rule, in which case the brackets are going to be the trace with respect to some quantum state and some commuting observables in here, so that it's something that you can actually produce in the lab. So this quantity is going to be R1. So R1 is going to be the product of xi, ix, xx plus R2 plus R3 plus C1 plus C2 minus, though, C3. In the quantum case, PM quantum is equal to, well, how did that work out? In the quantum case, you have that this thing, R quantum, is trace row A, B, C. Now in all the rows, this A, B, C multiplies to the identity so that this thing, because this is trace 1, also equals to 1, for example. So we have that this is 1, 1 plus 1 plus 1, plus 1 plus 1. And then here we had that, what is this one going to be? The multiplication of xx, yy, zz is minus 1. So this is also plus 1 equals to 6. What could we have expected classically? PM classical, I claim, is less than or equal to 4. How do I see that? So let's go back here and just sort of work through it very briefly. The idea is to say that with all the rows, you've defined a value for every single observable at least once. And now you're going to, when you go over to the columns, you assume that that same value goes over. So we already have that C1 is going to give a product to plus 1. C2 is going to product to plus 1. Now I argue that C3, in order for this to be 4, the reason it would be 4 is that you get a plus 1, plus 1, plus 1, plus 1, plus 1. But that if you had a classical model, the algebraic relations force this one to also be plus 1 as opposed to minus 1, meaning that it's 5 minus 1 equals 4. And then it's less than or equal to because you can consider like probabilistic mixtures perhaps. So let's see how let's see how this ends up coming out. It's sort of just rewriting what I already did, but the idea is that you break down v of xx, v of yy, and v of zz into quantities that we've already computed, or from the rows. So you have v of ix, v of xi for v of xx. This is v of iy, v of yi. And then v of zz is v of xy, v of yx. Now we're amply using the non-contextuality assumption, right? Because we're taking the values that we assumed in a different context, xi, ix, xx, etc., and reusing them in a context where, for example, xi does not commute with yy. So normally you would not actually be able to, in quantum mechanics, make this replacement. But in a classical world, or at least based on our definition that we're working with, you can make this replacement. Now, v of xy and v of yx can themselves be replaced with xi, v of xi and iy. So this is equal to v of ix, v of xi, v of iy, v of yi, v of xi, v of iy, v of yi, v of ix, which we have that everything shows up so that these are all showing up twice equals to plus 1, which is what I was arguing had to be the expectation for the third one under the assumption of a classical non-contextual value assignment. Great, so we have now we can think of the Peres-Mermin square as being formulated in a observable type of picture. There's a complementary and equivalent picture based on projections. Of course, you know, projections, so we want to consider rank 1 projectors, by which I mean projectors that project to a one-dimensional subspace. And in principle, the same exact definition of the V-map, this non-contextual value assignment, is going to be used. And of course, projectors are themselves Hermitian. So nothing prevents us from just applying that same definition to the case of projectors. There's some interesting consequences. So if you have just, say, a set of rank 1 projectors that are orthogonal, so pi 1 to pi d, say in a d-dimensional Hilbert space, delta ij pi I, then the spectrum of these things, so v of any pi I, is an element of 0 or 1. Okay, combine this with the second sort of structural fact, which is, and maybe I will sort of put this here, is that if we have that these are pairwise orthogonal, that they form a PVM, we have sum I equals 1 to d. We know that the projectors satisfy this, so then the non-contextual value assignment should respect the algebraic relations. So v of pi I is equal to v of I, let's be complete, equals 1. And I think that people see where this is going. Well, if I have that my value assignments are in 0 and 1, but that the sum of them are 1, then that means that there is some special v pi k which equals to 1, and the rest of them have to be equal to 0. I mean, this is a particular choice. This is a particular choice of the map V. Now, there are other choices. Perhaps you want to think of these different choices as something like a strategy. And the strategy is just a rule for picking which of these outcomes occur and which don't. And I think that there's a nice connection between some of the things that we've been talking about already earlier in the semester with ontological models. And so I want to make a remark to this end, which is something of the sort that we can interpret the non-contextual value assignments as an indicator function. In an ontological model. How does that work? Well, we know that, say that there's a set lambda, and we want to say that v of lambda, where little lambda is in this set, well, the different lambdas are different strategies, different ways of picking which of these projectors get mapped to 1 and which get mapped to 0. For instance, this might not exhaust all the possibilities, but just to give a little bit of an insight, well, this thing is between 0 and 1. I can interpret this as the probability of obtaining the outcome I, given that I have the strategy lambda. And moreover, this condition tells me that if I sum over v lambda pi I equals sum I p of I given lambda, that this has to be equal to 1 for every lambda in lambda. So this is precisely what we think of as an indicator. These satisfy the properties of an indicator function in an ontological model. So to bring this all full circle, what's going on here? we can think of a non-contextual hidden variable model. I mean, so when we prove, so something like the Peres-Mermin square or the Kochen-Specker theorem, how does this connect to our previous discussions? It connects in the following way. If we define an ontological model, and there can be some initial distribution P over the lambdas, but it really suffices to just look at the deterministic case. If we have a distribution over these lambdas, different ways to pick a strategy, and then these strategies are going to be deterministic and they want to respect the algebraic relationships of the quantum observables themselves, then what this is saying is that you can't, if you have a rich enough set of observables, like in the Peres-Mermin square, then it seems that you cannot even really define a ontological model that would reproduce the quantum predictions because there is not an indicator function that exists. That's kind of what the previous Peres-Mermin paradox was all about. And so this is also, I mean, you can rewrite the Peres-Mermin square paradox in terms of projectors and it works just as well. So this formulation, though, makes it clear that what we're really talking about when we talk about Kochen-Specker proofs or showing that there's no non-contextual hidden value assignment in quantum mechanics, it's a statement about indicator functions, and ergo, it's a statement about what kinds of ontological models are, again, allowed. And from a sort of high-level point of view, I think that it's worth noting that essentially almost all of the no-go theorems that we talk about in this course, we will also talk about the Pusey-Barrett-Rudolph theorem, which is another no-go theorem that people talk about. Almost all of them have to do with the structure of the indicator function, even the Pusey-Barrett-Rudolph theorem. And so I don't know if this is a controversial statement, but it is about the structure of the initial distribution in that case. But the reason that the whole proof goes through is because of the structure of the indicator function being dependent on this lambda. So, which is just to say that many of the no-go theorems that we've discussed in this course, and maybe almost all of them, are really about different types of indicator functions. In Bell's theorem, you had these product indicator functions. The fact that they are products allowed you to define, using Fine's theorem, a joint probability distribution. And once you are allowed to construct a joint probability distribution, it restricts the kinds of statistics that you can actually make for an empirical model so that you have this distinction between the classical and quantum regions. So the indicator functions are quite a rigid restriction, but at the same time, it's what we also think of as incredibly physically intuitive. I mean, the fact that the measurement outcomes are elicited by some ontic state, that there's an ontic causality, is in many cases precisely what we mean by something being classical or physical in some sense. So it is interesting to note that it is this thing that offends many, or is the root cause of many of the no-go theorems, which is maybe the most physical assumption. Okay, enough of a digression on that. Let's at least talk with or set up the Kochen-Specker theorem, although we will not prove it. The idea is to first work concretely in C3, and then for all d greater than or equal to 3, we can see C3 as being inside of CD. So the proof of Kochen-Specker is sort of, you can think of it as being embedded. So because C3 is a subspace, you can sort of rerun the argument for all d greater than or equal to 3. This, I want to say, without knowing precisely if it's true, that you can't rerun perhaps the same notion for Peres-Mermin, or it might not be as straightforward to show how it precludes a non-contextual value assignment for d greater than or equal to 4 in that case. I'm not sure. I think that's something I have to think about. An important part of Kochen and Specker's proof is that they want to restrict their attention to orthonormal if I knew how to spell, orthonormals vectors x, y, z in R3. I mean, historically, so the idea is that you can define a triple of, so if I have a set of orthonormal vectors in R3, I can define the corresponding spin operators Sx. And these don't need to be the Cartesian sort of basis. This is just any orthonormal set of vectors, Sx squared plus Sy squared plus Sz squared is equal to 2i. So you can define these spin operators. This is how Kochen and Specker did it historically. And consequently, you can also define a projector PL based off of this. So the important point is that for all orthonormal triads here, x, y, and z, you can define spin operators, and then you can define this corresponding projector, I minus SL squared, L equals x, y, z. Then you have that these two equations together imply that you have px. So you have a projector corresponding to one direction x, another direction, so I said p, pi x plus pi y plus pi z equals 2i. Why is this useful? It's useful precisely because I can think, instead of in C3, I can think of in R3. I have 3 orthonormal vectors in R3 that I can draw out. So this is useful for the proof technique. And these correspond precisely to 3 projectors that are also orthonormal. So it's nice to be able to say that these 3 R3 vectors correspond to 3 projectors that are also orthonormal, which helps us to sort of set up the crux of the argument. And perhaps it's not perhaps, it's almost assuredly the case that this helps you to actually construct the proof and see how the contradiction comes about. So, just as we had before, I don't want to sort of repeat myself too many times, but we use this setup where we are going to assign a 0, 1 value to each of these vectors. So, but because of this condition, for any given choice of v, you can only have one of them be 1 and the other 2 must be 0. And so how does Kochen-Specker come up with their proof? So broadly, introduce a set of orthonormal frames. I say orthonormal, I don't know if they have to be normalized. This is question mark. Set of orthonormal frames V F I equals 1 to n, say, and F I is some tuple xi, yi, zi of orthonormal vectors. Now define a commutivity graph. So I'll just say graph and we'll see how it's constructed First, we say that the set of vertices, so the graph G, the set of vertices are going to be the union of all distinct elements in here. And we say that mixing up notations, we say that, say U prime are in E if and only if the vectors are orthogonal in the Euclidean inner product. And then we also define a coloring. And what is the coloring? We say that some U in V is green, right? So we defined a set of orthonormal vectors, F. So I'm not going to tell you exactly how to pick these. There's a bit of an art, and symmetries can help in certain cases. But these are all pairwise orthogonal. And then you can define a set of vertices in a graph, which are just going to be the different vectors that you have. And you want to connect them by edges if they're orthogonal, which means that they commute. So this is a commutivity graph. And then we say that for a particular V value assignment, we say that some node is green if and only if V of P of U, I say P again, pi of U equals to +1. And we say it's red if and only if equals 0. So what is the problem that Kochen and Specker looked at? The problem was the following. V defined as above. That is not two colorable under the non-contextual value assignment that we define as being V goes from the set of vertices. Sorry, the notation's maybe not the best here. So this is the problem. You want to find a graph, so a set of vectors and that are orthogonal in a particular way, and then you want to show that this graph is not two colorable. So what that means is essentially that you're going to pick out in each frame something that's green and the other two are red, and you want to create a sort of assemblage or an arrangement of vectors such that you run into a contradiction, that a vector that was determined to be green in one context, that through a sequence of connections between different orthonormal frames or contexts, it comes back and that same green vector now has to be red, or vice versa. So that's the crux of the proof. And so Kochen and Specker did this for a Kochen-Specker set, as they're called, with 117 vectors, subsequently reduced maybe to 33 by Asher Peres, maybe 35 years ago. Adnan Caballo also reduced this further, I believe, to 18, which is the state of the art, so to speak. You can also do this. So you can do the Peres-Mermin square using projectors, and this will require, I believe, 24 vectors, if I'm not mistaken, which is precisely the number of stabilizer states corresponding to the 6 context rows and columns. So I believe for the most part that will conclude our discussion this semester of Kochen-Specker contextuality. So we might, although it's still a little bit flexible, we might talk about Speckin's contextuality. We'll definitely talk about the Pusey-Barrett-Rudolph theorem, and let's see what else. Thanks.